Now, 2 videos ago, we showed you that with systems, if we want to know what our output function is, we can just convolute our input function with our impulse response to get our answer, because we know if how our impulse changes, that is actually also how our input will change. However, the convolution and everything can still be very tricky and still very confusing. So maybe, can we do this better? Well, actually we can. And this is a small part of the Fourier transformation, and in the next video we'll tell everything about the Fourier transformation that we were learning in this course. But for now, we'll take the half approach and assume that our x input, our x of t input, is equal to the form of e to the power I omega t plus phi, which can be rewritten as a times e to the power I phi times e to the power I omega t. Well, the x convoluted with h, let's actually write that out. So we get minus infinity to infinity of x of t. Well, let's do it the other way around, actually. Let's write down h convoluted with x. And it does not matter, but for writing down right now, it just circumvents some of the hassle that we might have. So this is the impulse response with s multiplied with the input function t minus s ds. This is equal, if we fill in our generic function, the form that our input must have, we get that this is a multiplied with e to the power phi, I phi, multiplied with e to the power I omega, and t is t minus s ds. This is equal to the integral of minus infinity to infinity of h of s multiplied with a times e I phi to the power of I phi multiplied with e to the power I omega t multiplied with e to the power of I omega or minus I omega s ds. We've just split up all the powers in the e and just rewritten them as new e powers. However, our a, our e I phi, and our e to the power I omega t are not dependent on s. So actually we can take that out. So we get the integral of minus infinity to infinity of our impulse response multiplied with e to the power minus I omega s ds, and then this multiplied with a times e to the power I phi times e to the power of I omega t. But this was actually our input, our original input again. And this is actually rewritten our impulse response into the frequency domain. Because right now we have something with an omega, with a frequency in there. So we have found something anew. We have found that this is equal, our y of t, our output is equal to our frequency impulse response in the frequency domain multiplied with our input. So now we just have to multiply, only if our x is of this specific form, but then we can actually multiply to get our answer. And this multiplication actually helps us with the computations. So let's actually do an example where we do it via the old way and one via the new way. So you can see that actually the new way can be much easier. So we have x of t, which is 2 times the cosine of 5 pi t. And then we have our impulse response as e to the power of minus t times the step function. Oh, not an s, but a bracket. Yes, there we go. So let's do it in the old way, just convolution, the boring old convolution. X of t convoluted with h of t is equal to the integral of minus infinity to infinity of 2 times the cosine of 5 pi s multiplied with e to the power of minus t minus s multiplied with u t minus s ds. This is equal to, we can take the 2 out, so we get 2 multiplied with, and if we recall the Euler formula, if we look at the cosine, we can say it's actually the real part of the whole number. So we're looking at the real part of e to the power of I 5 pi s and close the bracket. We're just looking at the real part of this number. And then we have e to the power minus of t minus s, which we can rewrite as e to the power minus t multiplied with e to the power of s. And once again we have our step function, which we can use to actually remove or change our boundaries, because t minus s should be equal or bigger than 0, and like we have seen in the last video, that we know that s should be smaller or equal than t. So with this we can actually change our boundary, our upper boundary, until t. We have the real part of e to the power I 5 pi s, and we have multiplied this with e to the power of s. So we do plus s, and then we still have e to the power of minus t ds. Now in the next step we're going to remove the e to the power of minus t outside the integration, because it is not dependent on s, and there's no variable s. And we're going to rewrite what's inside our real part. So we get 2 times e to the power minus t multiplied with the integral from minus infinity to t of the real part of e to the power of s, open a bracket, 5 pi plus 1 multiplied with ds, like this. And then we're going to integrate. Because the integral of this is equal to 1 over I 5 pi plus 1 multiply with e to the power of s I 5 pi plus 1 from minus infinity to t. If we fill it in to the right over here, we get 2 times e to the power of minus t, the real part, where we fill in t for s. So we get 1 over I 5 pi plus 1 multiply with e t I 5 pi plus 1, like that. That is the real part with t filled in. And if we fill in negative infinity for the other part, then we get negative infinity in the power, where we have the s over here. And if we have something in the power of negative infinity, it will actually go to 0. So we get minus, where we fill in negative infinity, which is 0. Now, we can take out a small part and put in the e to the power of minus t. So now this is equal to 2 times 1 over I5 pi plus 1 multiplied with the real part of e to the power of t. Well, actually, let's work out the brackets, because we get what? I 5 pi t plus t, but if we add the minus t again, we get minus t here. So these actually cancel each other out. And because we have taken the real part, we can rewrite it back to a cosine. So we will get in the end our answer of 2 divided by I 5 pi plus 1 multiplied with a cosine of 5 pi t. So we finally get our answer. Yes. Okay, now let's do this way easier. Recall xt is our 2 times the cosine of 5 pi t, and our impulse response was equal to e to the power negative t times the step function. Well, let's first calculate what our h omega will be, because we could just do xt multiplied with the h omega. What is our h omega? It is the integral of minus infinity to infinity e to the power minus t multiplied with the step function multiplied with e to the power minus I omega t dt. This is equal, well, the step function again changes the boundary, but this time it changes the lower boundary, because the step function always returns 0 if t is lower than 0. So we get from 0, integrate until infinity, e to the power of minus I omega t minus t dt. We can rewrite this power once again to get e to the power of t. Open up the bracket where we get, oh, actually let's do minus t to make it easier. I omega plus 1 dt. We'll fill this in, or we integrate this, where we get minus I omega plus 1, and 1 divided by this, multiplied with e to the power of minus t I omega plus 1. Now we fill in 0 and infinity. Well, if we fill in infinity, again we get a minus infinity in the power, which will result to 0 minus I omega plus 1 in the denominator, 1 divided by that, e to the power, well, if we fill in 0, then the whole power will be 0. So actually we get e to the power 0, which is just 1. So this is just equal to 1 over I omega plus 1. Now we multiply this with our input, with x of t, so we get the following. 2 divided by I omega plus 1 multiplied with the cosine of 5 pi t, close bracket. However, why we can only do this when our input has a specific form, because we know that our input has an omega of 5 pi, so we can fill that in for this omega, resulting in our final answer of 2 divided by I 5 pi plus 1 multiplied with the cosine of 5 pi t. And this answer is exactly as the same as the answer that we got up here. And as you saw, this answer was much more easily computed than what we did above here with the convolution. Now, this nice and neat little trick of changing our impulse response into the frequency domain is not just limited towards the impulse response. And we can use that on the other functions as well. And those are really called Fourier transformations. And we will talk about that in the next video.